So let's think of a industrial device, right, where we might have a, like a motor mount or something. But let's just kind of give it a mass. And then we have two fixities, and let's put some rubber offsets in it, right? This is kind of a rubber beam. Doesn't look very rubbery. Maybe I'll just label it as rubber and rubber. That seems like better, right? So let's assume that the rubber dampers add damping, but no stiffness. So we need some stiffness from another source. So let's add a strut where we have a spring at an angle, right? And that spring is going to have an angle alpha. All right. So the first issue here is when and let's consider that x is positive down, right? So we have 1 degree of freedom, which is going to be x in the vertical axis. That makes sense? So the first issue is what about alpha? Does alpha change as x moves? And we could have it change as x moves, but that gets kind of complicated. So let's make the assumption that the spring is long enough that alpha is unchanged. Right? So if our spring is at an angle, and our damper, our spring is at an angle and our dampers don't add any stiffness, that kind of becomes something that we can start to solve for. What is our first step that we want to do here? If we want to solve for the natural frequency of this, what's our first step going to be? What was that? Get our equation in motion. Yeah, but even before that, yeah, we want to draw out a free body diagram, right? It's a good way to solve all of life's problems. So let's do that. Because we're acting in the vertical direction, right? We're probably going to want a mass that looks something like this, right? So this is our fixity. So our spring is at an angle, but what about our dampers, right? We assume that these add damping, but we only have 1 degree of freedom, right? So we can't really add a damper in this direction. That doesn't make sense, right? So we need to add a damper vertically, and so let's go ahead and do that. Actually, let me make sure I phrase this problem right. Yeah, so we want to get the natural frequency in the vertical direction, right? So we want omega n and omega d, if we can get it. And then we have our stiffness here, which is going to be provided at an angle. Right, K, and then we have alpha in between the two. We're definitely going to need to know what the other components of that is, right? Once we have an alpha that's an angle, we're going to want to define our vertical distance as h, and then the length of the spring is L. So this leads us to our free body diagrams. We need to do one in an equilibrium position. Right, so we have our mass, and then what's the force acting down on it? Force of gravity, right? So mg Do we have any force acting straight up on it? Straight up, so not at an angle, like perfectly vertical? No, right? Because our damper is only a function of velocity, right? And so, but at an angle, we have K delta. But that's offset by alpha, right? And so for our displaced force, we still have mg acting down. But now do we have a vertical force acting up? Right? So we have to get our damping in here, because we have to get damping into the equation of motion. So it's got to be in our free body diagrams if you're thinking about it. So yeah, we're going to have a damping force. And what's the force from damping? How do you compute that? C equals what? Or sorry, F equals FC, but capital F, lowercase c, CV, yeah. So Cx dot, same thing. How's that?
I just have a question about the equilibrium condition. We don't have to account for the horizontal forces because we're only in the x.
So we only have, there's multiple ways to answer that. We only have the 1 degree of freedom, which is vertical. So a horizontal force isn't going to affect it. We didn't really define any horizontal forces, but if you wanted to say that there's horizontal forces, so one way you could say we're only concerned about the x and the horizontal forces we never defined. The other way you could say it is I've got forces on both sides, but my damper is the same on both sides, so they're going to cancel out. I would take either of those.
If we don't care about the horizontal component of the spring, we just assume it's vertical.
No, but our stiffness of the spring is composed along this line. So if you buy a spring at 10 pounds per inch, right, the angle you put it in matters. That make sense? So, but for these equilibrium positions, the horizontal forces don't matter. If that's what you're talking about, like forces on the side here. Okay, so go ahead. But
is there a reason why we have to spring sideways? Is it like a modeling situation, or is the problem just given like that? Because like, why are we not having the spring and the damper parallel to each other?
Because that's not how it was given.
Okay.
Yeah, that'd be too easy. We did the hard one.
All right.
So, because it, educationally wise, it gives us something to talk through, right? So it allows us to ask these hard questions, you know, about what are the cases, like the horizontal forces and things. That makes sense?
Yes.
Okay, so now we have our force here at an angle. And so what is this force going to be? It's going to be K times our displacement, right? But it's displacement of the spring. So it's going to be K times what goes inside the brackets. Okay, so this delta, I like that answer. But does the spring stretch x?
No, it's a component.
It stretches the component. So it's let's call it delta L, right? Because we defined it plus capital delta L. Because we defined L as the length of the spring. That makes sense? And we'll get that component out. But first, let's see what cancels out, right? Because before we get too far into the math, we know that from our equation of motion, our equilibrium delta is going to cancel out, right? Or should. Sure hope it does, otherwise I'm going to look like an idiot. Yeah, it does. So first, thing is we need to do is do our Hooke's law. So positive down, the sum of forces in the x is equal to mg minus k delta cosine of alpha is equal to 0. That makes sense? The sum of forces in our x, so we're just worried about this x component of our spring. Okay? And then in our displaced state, we still have positive down. Sum of forces in the x is equal to mg. Positive is down, so cx. What in the world? Cx dot on top is got to go negative, so minus cx dot minus k, and again we only want our x component of this triangle, so it's going to be k cosine of alpha times our hypotenuse, which is delta L plus lowercase delta. Right, so applying Newton's second law, we can cancel out some forces of this, and our equation of motion becomes mx double dot plus cx dot plus k delta L cosine of alpha is equal to 0. That makes sense? Right, so there's a little bit more here that we can do. Looking at our triangles, right, particularly this one where we have H and L. Well, we have a cosine of alpha in our equation of motion. So we have cosine of alpha in our equation of motion. And for relatively small angles, right, we can show, and that the displacement, we're going to assume that alpha stays the same, right? We can show that that's just equal to H over L, which for a small displacement that's going to, where alpha stays the same, that's going to equal to X over delta L. Right, so I'm just going to kind of say that for our given X displacement here, our delta L is going to be relatively the same. And that's a true statement if alpha is small enough. No model is perfect, right? Some models are useful. So, however, what we can do then is pull that down here into our equation of motion, and we end up with mx double dot plus cx dot plus k delta L times x over delta L is equal to 0. And that can simplify down to by canceling out our delta L's, which is mx double dot plus cx dot plus kx is equal to 0, which actually just gets us right back to where we were before. Right? So now if you want to know your damped natural frequency, it's omega d is equal to omega n, the square root of 1 minus zeta squared. So that seems kind of hand wavy, right? But just showing you that we can get, it's not obscene assumption to just assume that those are the same. So we get back to our same natural frequency.